Okay, so we will continue studying this hypothesis testing. And until last time, we studied the testing the mean, right? Whether the mean is the same between the two when the variance is known. But in this case, it's kind of a natural flow that we saw in the interval estimate, which was transitioning from known variance to unknown variance, where we have now this t statistic. And so the assumption or the two hypotheses is these two. It's in this case we are considering just a single distribution, and we typically assume a fixed known value, like the person's height is the average is 175, so this value is fixed. But our sample is saying that, okay, so this may be wrong, right? So this may be different from this known value of 175. So so in that case, how can we handle this problem? So in the previous case, we used the test statistic of this guy, x bar, and then sigma divided by n, that followed the standard normal distribution, right? So in this case, we change this guy into our sample standard deviation, and then in that case, minus mu 0. So in this case, if we replace this guy with this, and then it will follow the t distribution, but the degree of freedom will be n minus 1, where n is the number of observations in our sample. So in the case of two-sided test, where the null hypothesis is this guy, and then this alternative one is just simply saying that it's different from mu 0, and then it's a two-sided test, and so we have to distribute the probability or alpha value of 5% into 2, and then that's why we have alpha over 2 and n minus 1 as a degree of freedom. And so if this test statistic, which is this guy, where we replaced the sigma with this s, if this guy exceeds this value, and then that's when we reject this null hypothesis. And then what was the p-value? So in the case of p-value, we first ignore this value, right? So we assume that this alpha value is not given in advance, and then given this t distribution, then we compute this test statistic, and then that value, if that value was placed here, and then we compute these probability of observing this value or more extreme values, right? So that was the p-value. Okay, in the case of a one-sided test, so we want to claim that our mu is greater than mu 0. So that's the claim that we want. In that case, the acceptance region will be something like this. This test, acceptance region will be test statistic, which is this guy. So this is our test statistic, and if that is smaller than a particular value, maybe let's call it as c, which was our critical value or the threshold value, right? So if that was smaller than this critical value or the threshold value, and then that's when we accept the null hypothesis. But if TS or test statistic is sufficiently larger than this threshold value, and then that's when we reject this null hypothesis, right? And then the corresponding p-value will be yeah, in the case of t distribution, if we observed this value, and then this part will be our p-value, right? Okay, so let's look at the example. Yeah, so this example is quite lengthy, but yeah, don't get confused by this irrelevant expression. So yeah, it has nothing to do with how to solve this problem, but these are the main part of this problem. So these are the statistics, and then we want to prove that, or we want to show that these measurements are greater than 8 minutes, or the average measurement, right? Mean service time is greater than 8 minutes. So in this case, the situation is that we do not know the variance, and so we have to use t statistic, and then we first have to compute the x bar and s, and then x bar minus 8 divided by, yeah, so let's count it, and then yeah, it's 28. So we compute this sigma. Yeah, instead of sigma we compute this s, but what was the denominator here? Should it be 28 or 27 or what? What was that? 28, right? So 27 was used in computing s, or s squared, right? Yeah, so again, in this representation, we just simply replace this guy with the s, but still this denominator of square root n is still the same, so it's it should be 28. Okay, and then we compute this test statistic, and then yeah, so in this case, yeah, we can compute this p-value, and then decide whether to reject or not the null hypothesis. Okay, then let's move to like two different distributions. So here we are not given a particular mu0 as a constant like this. So in this case, it is simply a constant value that is known in advance. And also in this example, we were given this particular value that will form our null hypothesis. But in this case, we are given two samples composed of this x1 through xn, y1 through ym, respectively, and then we consider their true mean, and whether they are the same or not. Okay, and then yeah, we compute this, right? And then let's see, yeah. So here we assume that the variance is known. Variance is known for each of these two populations, and then they are not necessarily the same. So the first one has the variance of sigma x squared and sigma y squared, so they are known value. And then what is this guy following? I mean, what kind of distribution does he follow? So in this case, mu x minus mu y, these are the true parameter, right? And so altogether, this statistic will follow, have the mean value of this. And then what was the variance of this guy? What was the variance? Now what about the variance of this guy? It was, yeah, so the number of observations for these two samples were n and m. Okay, so in this case, it will have the variance as sigma x squared divided by n, right? And this guy will have m sigma y squared over m. And then since these two are independent, and then the sum of these two will be the variance of this guy, right? Yep. And then we assume that each of these populations are normal, and thus x bar and y bar are also normal, and their sum or the subtraction between them will also be normal. Yep. So we basically compute this statistic. Yeah. So we have this statistic, but we have to subtract mu x minus mu y, right? Where is this guy? Where is this guy? Why do we not see this value in our test statistic? Why do we not see them? So this, yeah. So we start, yeah, we assume that this null hypothesis is true when computing the test statistic, right? So we are assuming this situation, right? And so this one will be 0. Okay, and then altogether this guy will follow the standard normal random variable. And then, yeah. So here P of H naught means we compute the probability assuming that H naught is true, or the null hypothesis is true, right? So that's the meaning of this notation. Okay, and then, yeah, this inequality can be represented as this one. So we simply put the absolute value operator in this. And then if this is within this z of alpha over 2, and then that's when we accept the null hypothesis and then reject it if it is greater than this value. Okay? Okay, then in this case, the type 1 error, or the maximum error that we can allow as type 1 error, okay, maximum possible type 1 error was by definition alpha, right? And then what about beta? What about beta? So in this case, it's just like the one population case. So when computing this beta, beta was dependent on the true mu value. So in the case of H naught, which is mu was mu 0, and HA alternative hypothesis, or H1. So H1 or HA, so they are just used interchangeably. So they are basically the same thing. In some books or some problem sets, people says or use HA, which denotes the null as a null alternative hypothesis, or H1. Okay, so mu is not mu 0. So in this case, mu was our parameter that determines the probability of type 2 error, right? So in this case also, we consider this and this situation in the alternative hypothesis. So we have to introduce the parameter as mu as maybe mu x minus mu y, and then our beta will be the function of this mu value, right? So again, in this case, so mu x is not actually mu y, but they are really close. So they are certainly different. I mean, so yeah, we often say oracle. Oracle means, yeah, some kind of god, God that knows everything. okay, who knows everything, okay. Yeah, so Oracle is often used in also in machine learning concepts as well. But anyways, so so only Oracle will know the true parameter value. But suppose Oracle knows that these two are different, so certainly this alternative hypothesis should be true. But they are having really small difference. Mu x may be 174 and mu y maybe 175. So in this case, yeah, the rejection region or the acceptance region is completely determined by the null hypothesis. We already learned that. And in that case, even if they are different, but their gap is really small, and so yeah, in this case mu will be just only 1 centimeter, and in this case the probability of beta will be really small. Sorry, really big, right? Okay, so yeah, so that was testing whether the two means are equal from the two normal populations. Okay, and then let's look at this example. Yeah, so example is typically really long, as I mentioned maybe a month or so ago. Yeah, but you have to find out what are the key values or key aspects or information that you have to use to solve this problem. Okay, so we have two populations. I don't even know what they are, but we have two populations, and then they are normal, and then they have a standard deviation as this guy, and then also B has a standard deviation as this guy. I don't know why they didn't use the same sigma here, but yeah. But anyways, and so so testing the hypothesis that there is no appreciable or no real differences in terms of the mean life of these tires. So these are the observed life duration of tires from A and B. Yeah, and then we can correspondingly obtain NMN, and then this guy has 4,000 as a standard deviation, and then 6,000 as also another standard deviation from for the group B or population B. Okay, and then we can just compute this value, right? We can compute this as sample mean from X and sample mean from Y, and then we take the difference between them and then divide it by this value. So that will be our test statistic. Okay, and then we apply this Z, or standard normal distribution. Okay, and then next thing is the case where the variances are unknown. But if you remember the previous chapter, when the variance is an unknown and when considering two different normal distributions, and then although we do not know their variance, but we assume that they are the same, right? They are the same. And then what we used was something called this guy, which is a pooled variance, right? Pooled variance. And then the definition of this pooled variance was this guy. So we compute this sample variance from each two of these sample, and then multiply with this degree of freedom, because that was originally in the denominator of the definition of our sample variance. Okay, and then if we divide it by sigma squared and then divide it by sigma squared, and then what was that? What kind of distribution does it follow? So this guy was xi minus x bar squared, right? And then we consider this sigma divided by sigma squared, and then it was following the chi-square distribution, right? What was the degree of freedom? So we had an n observations, and thus the degree of freedom was n minus 1, right? And then this part will also be chi-square distribution with the distribution of the degree of freedom of m minus 1. And then if we sum them up, and then altogether we have a degree of freedom as this value, right? So the story is almost the same. Okay, then by the definition of this pooled variance, we had this guy, right? Okay, so yeah, let's see. Let's see if we have. Yep. So let's look at this summary table. So this was the test statistic that we used when the variances are known, but they can be different variances. Sigma 1 squared, sigma 2 squared. And then in the case of they are unknown, but assuming that they are the same, and then these two will be the same, right? And then it will be like sigma squared, square root of sigma squared times this, right? The denominator will be equal to this, right? And then conceptually or intuitively, we replace this true sigma value, sigma squared, with our pooled covariance, pooled variance, right? And then the remaining part will be the same, right? So if we replace this value with our pooled variance, and then this one will follow the t distribution with the degree of freedom of what? N plus m minus 2, right? So that's why we see this value as a degree of freedom of a t distribution. Right? So yeah. So I honestly think that you guys can remember all these equations. Yeah. So I didn't allow any cheat sheets in the last semester. I mean, maybe a year ago, even at the final exam. But I heard that many complaints from the students. And then there was another class teaching where the same class, same subjects were taught, and then they allowed the cheat sheet. And then I heard even more complaints. Anyways, I will allow one sheet of this cheating paper, but if you have this kind of intuitive story, high level story, and then it should be doable. I mean, to remember all these equations. Okay, and yeah, you can compute the p-values as well, right? Computing your test statistic, and then suppose that value is v, and then we can compute this p-value. Yep, and then we have these two samples, and then the variances are unknown, but they are assumed to be common or equal. Then Yeah, you can. Yeah, you should be able to follow this example easily. Okay, and then let's move to the next. I mean, probably the most difficult situation where we have unknown variance, but also we do not assume they are equal. So yeah, they are assumed to be unequal. Okay, so in that case, can we use a pooled variance? So pooled variance is no longer usable, right? Because pooled variance was kind of an estimator for our common variance when we do not know this variance value. But if they are not equal from the two populations, I mean the variances are not equal from the two populations, and then the pooled variance will no longer be representing one common variance. So in that case, we have almost no option to model this situation. So in this case, we can define some really complicated test statistic, but it's out of our scope in this class. But the solution that we do in handling this case is really simple. So we have two samples which has two different means and which has two different variances which are also unknown. In that case, we assume that n and m is really large. Okay, so they are really sufficiently large value. Okay, and in that case, so this value is basically an estimator. So this is called a sample variance, right? And then it's an estimator of our true parameter sigma x squared, right? But if n gets larger and larger, then this value will approach to or converge to the true value sigma x squared, right? And why is it so? I mean, let's try to prove that. Okay. Why is it converging to this true value? So again, xi minus x bar squared, I equals 1 through n, and then divided by n minus 1. So this is our definition of the sample variance, right? And then how can we model this statistic as a particular random variable distribution? I mean, I'm doing really the same thing over and over, but n minus 1 times this value, so we cancel this out, s squared, and then divided by sigma squared, or sigma squared, the true value. So that will follow what? That will follow chi-square distribution. And then do you guys remember what was the... So it is a chi-square distribution with the degree of freedom of n minus 1. What was the mean and the variance of this case? Mean was n minus 1. It is really simple. It is simple because so this guy, so it's like the summation of zi's. So by the definition, zi squared and it's a sum over I from 1 through n. So that was the definition of the chi-squared distribution. And then the expectation of it will be the expectation of n times expectation of zi squared, right? So we are just reviewing what we already learned. And then what is this value? So this one is basically the variance of zi's, because it can be viewed as zi minus 0 squared, right? And then what is this guy? So it can be viewed as this, right? So this one is basically the variance of zi. You guys understand, right? So what is the variance of zi? Zi is a standard normal random variable. So the variance of it will be 1, right? And so this value will be 1. And 1 times n will be n. So chi-square distribution will have the mean value as n. But in our case, it was the chi-square distribution of the degree of freedom as n minus 1. So accordingly, the mean value will be n minus 1, right? But what about the variance? Can anyone tell me? So we didn't prove that. Yeah, we cannot prove it, but can anyone tell me or give an answer for the variance of this chi-square distribution? So in the case of the degree of freedom as n, the mean of a chi-square distribution was n, but what about the variance? What about the variance? You can just look back at your book. It was about, not about, but what was that? Okay. So mean is k. So in that case, k is the degree of freedom in this case. And then the variance is just 2k. So variance is 2k or 2n. Although we didn't prove that, but yeah. So that is a property. So we saw this shape of the distribution, right? So the mean value will be shifting towards the right as the degree of freedom will increase, right? And then also the variance will also increase, right? So having a wider and wider distribution, right? So we learned that, right? Okay, then in this case, the variance will be 2 times n minus 1. So that will be our variance of chi-square distribution, right? Okay, then so this value will have the chi-square distribution. It will be the chi-square distribution, and then it's let's consider this the variance of it, okay, and then okay, n minus 1 squared. This guy will be chi-square distribution of an degree of freedom of an n minus 1, and then let's think about this variance. So yeah, so in this case, what was the mean value? What was the mean value? In this case, n minus 1, right? And so we subtract the mean, and then let's call the variance of this guy as maybe k, and then okay, so yeah. So this guy is this guy, And so this guy has the variance as, yeah, so this guy's the variance will be like n minus 1 times 2, right? So please forget this. And then this will be true, right? And then we are interested in the variance of s squared, okay? Then it will be represented as this, right? So we know when we have this guy as maybe k, and then what is the variance of x? So we simply multiplied it or divided by a, which is a constant, so a squared, right? Yeah, so it's quite easy, right? And so this guy's variance is this guy, and then we are interested in this guy's variance, s squared, the variance of an s squared. And then what is this a in this case? A will be this guy, right? And thus 2 times n minus 1 times n minus 1 sigma squared n squared, right? So that is the variance of this s squared, right? So n gets really large, so in that case what will this value be? So what kind of value does it convert to? So n becomes infinity, and thus, yeah, so we basically have this guy, so 2 times sigma squared divided by n minus 1, and then, yeah, even though we do not know sigma squared, right, this is just a constant, and then n minus 1 will go to infinity, and thus the variance will go to infinity. Variance will go to 0, right? So what is the meaning of the variance of s squared? S squared was basically an estimator for our true variance sigma squared, right? What was the variance? So from the same population or the same distribution, I obtained my own sample, like a 10 person's height, and another guy obtained his or her own 10 person's height. Okay, so in that case, I have my own sample variance as an estimator for the true variance, and then the another guy will have his or her own estimator for the sigma. So it may be different, right? So the variance will be like how much they are different between this sample statistic, I mean the estimator, and also my true parameter, right? So this guy was like maybe 10, but in my case, I computed my sample variance as 12, and then the other guy obtained as 8, and the other guy obtained 11 or 13, and so on. And then what is the average deviation or the standard deviation or the variance? Okay, so that will correspond to some error contained in my estimator, right? So in this case, let's suppose n goes to infinity. So it means that I obtain maybe hundreds of thousands of observations in my sample, and then the other guy will also obtain hundreds of his or her own hundreds of thousands of observations. In that case, I compute my own sample variance, and then the other guy will compute also his own sample variance. And then what will be the variance? What will be the variance? What will be the average differences like these? So as this says, s squared, it is also a random variable, right? And then it's a scaled version like this, will be chi-square distribution. And based on the fact that this chi-square distribution will have the mean and the variance as n minus 1 and 2 times n minus 1, we can compute the variance of our own estimator, and we show that our estimator had a zero variance as n goes to infinity. So in that case, I mean, in the case where I obtain hundreds of thousands of samples, and then the other guy also hundreds of thousands of samples, and then those two different sample variance will basically be the same, right? Because n, the sample size from each of these two samples, were really big. Okay. So this was, yeah, this is another property of this estimator. So we learned or studied the one property of an estimator, which was biasness. So unbiased estimator or the biased estimator, right? Do you guys remember? And then another important property of this estimator is about this. So if n gets larger and larger, and then our sample statistic or the estimator will converge to the true parameter value. Let's see. And then that is called a what? That is called a what? So let me see if I can find the term. Okay, yeah. Among these, the third one, consistency. So if your estimator is consistent, and then it means that as n gets larger and larger, your estimator will have a zero variance, and also zero variance means even though you have a different samples, and then your sample statistic or estimator will be just a single value. Zero variance means what? The distribution will be really sharp at the single observation value, right? In that case, that value will be the true parameter value that we want to estimate. So in that case, it is called the property of this consistency. Okay. So we have this unbiased estimator, and then this consistency. Then what about this? So your estimator is a biased. Okay, your sample is your estimator is a biased, but also your estimator is consistent. Is it possible? I mean, yeah. Is this case possible or not? So let's think about the unbiased estimator. So it means you have, so your true parameter mu was 175, but your sample statistic, x bar, and its expectation value is maybe 173. So on average, your estimator is like underestimating the true parameter value, right? So in that case, if we use sample variance as like sigma xi minus x bar squared and divided by n, in this case, it was an unbiased, it was an example of biased estimator, right? Your sample variance was maybe 10 centimeter, but this guy, I mean the average value of this, so this is the true variance value, but this guy, if you compute this statistic, and then on average, this one maybe will give maybe 9 or 8.5 centimeter or something like that, right? So in that case, So even in this case, the variance of this estimator will go to 0 as n goes to infinity. Do you understand this? So what is the difference between this guy and n minus 1, like this guy? So this is just a difference in terms of n times n minus 1 or something. So this one has just a different in terms of this ratio, in terms of this fixed ratio, right? Fixed ratio. So you already saw that this guy will have 0 variance as n goes to infinity, and then this guy will also have 0 variance as n goes to infinity, right? And then, yeah, so if n gets larger, if you happen to use this estimator, and then it will give just a fixed value. If I get hundreds of thousands of observations in my sample, and another guy has his own hundreds of thousands of samples, and then if we compute this value, and then my value and then the other guy's value will be the same basically if n gets really large. But these converged value will not be the same as our true parameter value because they are unbiased, right? Okay, so back to our slides. So my point was, if n gets large, and then your sample variance will have really small variance, right? As I mentioned, by considering like hundreds of thousands of observation cases, so the sample variance will be just obtained as a single constant value because the variance is really small for it. And then such a value will be just the same as sigma squared because they are unbiased estimator, right? Okay, and then yeah, if n gets really large, and then you can just assume that your sample variance as the true parameter value because it will have 0 variance or very, very small variance value. So basically it will have very small error from the true sigma squared value, right? So we can just use this guy, instead of this value. So this one, yeah, when n gets large, again the situation is the sample size from the two groups were really large, and n m n are considered to be really large, and then the variance are not known and they are not equal. But even in that case, we just use these two different sample variance as just a true variance value, and then use the same equation or same test statistic. So so we already understood this, right? And then we just simply change these two by those two approximate estimate, but if because n and m are really large, and those two will be almost the same as these two values. Okay, so yeah, so we use this really simple ideas, and then construct or form this test statistic, and then we model it as what? Instead of t distribution, we model it as standard normal random variance, right? Because we assume that these are no longer be a kind of a chi-square distribution or whatever. They are just assumed to be like a fixed value because yeah, n and m are really large values. Any questions so far? Okay, and then the next topic is about paired setting. paired setting. So we still consider like two different populations. Okay, and then we are concerned whether their mean are the same or not. Okay, but in this case, those two the observations from one sample and then the second sample are actually paired. So in this case, like so so this can let me give an example. So let's just compare or collect one sample from like 10 people from Korea, and then another sample by collecting another 10 people from the US. So we have two different sets of 10 people from Korea and US in the US respectively. So they are really different people, right? And then we can apply whether their mean are the same or not, depending on these different situations. So we consider the three different situations, but all in these situations, we are concerned about the testings, about the test whether the means of these two populations are the same or not, even though they can be like a one-sided test, right? But in this case, the situation is a little bit different. So you can imagine the following kind of situation. So we pick up 10 people, maybe 10 people who are already fully grown up. Not sure if that is a good example or not, but so 10 people we collected are actually they have moved to the U.S. Okay, and then we wait for maybe another 10 years. Okay, and then see if some other like a food or other lifestyle affects their height. Okay, so we have the same 10 people between the first population and then the other population or the sample. Okay, so that is this paired situation. And then also, maybe it may not be a good example, but maybe you installed some tires, and then I don't know, but you actually maybe injected some. It's a little difficult to come up with a good example, but you installed some 10 tires from into 10 cars, and then you did something into each of these cars. Maybe you injected your new medicine to this car, and then you also measure maybe in a week or in a month. You measure there are actually some changes in these tires due to your medicine. So in that case, you are looking at the same car one by one. You have 10 cars initially, and then the same 10 cars are existing in the second sample. Okay. So that is this paired statistic. So in this case, you installed something, and then some pollution control device were installed into the car, and then maybe you measure how much like bad air, bad pollution is emitting from these cars. Okay. So you have the situation. You now understand the situation. Okay, and then we are now interested in this statistic, which are basically the difference of these two measurements in this paired setting. So we can simply measure the difference of these person's height of the same person. So the person with the height of 175, he became like a tall with the height of 177. And then the other guy having the height of 170, and then this guy actually had the height of 168 or so. So sometimes this height will increase or decrease, but we can kind of measure the difference based on the same guy's difference changes in terms of this height. Okay, so yeah, we can measure the difference. Okay, so after computing these differences, and then we can now consider it as a single population or single kind of sample. Okay, and then our hypothesis that we are interested in testing is whether the mean of these differences are 0 or not. Okay. Yeah, and then the remaining story will be the same, but yeah, so it's a easy thing. But let me ask this situation. But yeah, let me ask this situation. So in this paired setting, is it possible that the sample size between these two sample different or not? So is it possible that the sample size are the different between the two samples? So in general, in these examples, or maybe we collected 10 people's height from Korea, and then maybe 25 people from the US. It is of course possible, right? It had no problem or no issue. But in the case of paired setting, can the number of can the sample size of one population be the different from that of the second one? Can they be different or not in the paired setting? So these two should be the same person or same car, and then these two also should be the same person or car, right? And so we have to have the same number of observations, and they are actually paired, right? And so it is not possible that one sample has more observations than the other, right? Because in that case, it's no longer be a paired situation, right? Okay, and then yeah, so here our assumption is individual xi and yi's are all normal, and then correspondingly the difference between the two normal random variables are also the normal. And then we can, let's assume that we do not know the variance of them. In that case, we can use the t-test or the t-statistic, right? Yep, and thus, we basically compute this wi, which is an xi minus yi, which can be viewed as maybe the height difference of the same person among the 10 people who moved from Korea to the US. And then we have basically 10 numbers, and then we compute wi bar, or the sample mean, and then the sample variance of this wi's, right? The sample variance. So if we had 10 people, and then we just compute this guy, right? Wi and wi bar squared, right? And so we can obtain this sample variance of our wi's. And in that case, we can use this guy, wi bar, wi minus 0, because we are interested in the null hypothesis of xi bar, x bar equals y bar, which means w bar is 0, or so mu x equals mu y, which means mu w is equal to 0, right? So that is the null hypothesis, right? So w bar minus 0 and sigma divided by n should be our sample statistic following z distribution, but we replace this sigma with our sample variance or sample standard deviation, and then we can change it with the t distribution with the degree of freedom of an n-1. So if we had 10 people, then the degree of freedom will be 9. Okay, so that will be our test statistic. Then we apply it to this t distribution. Then we either accept or reject the null hypothesis. Okay, so we have these and these paired statistic, and then we take the difference between them. Okay, then we can perform this hypothesis testing whether the mean of this guy is 0 or not. And then also we can do one-sided test as well. Okay, and then the next one is testing about the variance. Okay, so far we discussed all the different situations, but commonly we tested about the mean, right? Whether it was a single population or the two populations, but we were testing about the mean. But now we are testing about this variance, and we have we have one population here, and then we are interested in whether their variance are actually the same as this known variance. Okay, and then so here in this case we use this sample statistic as our test statistic based on this formula. So we assume that the null hypothesis is true. So we basically compute this sample variance, and then times this, and then divide it by sigma 0 squared, and then it will be following this chi-square distribution, right? Okay, then so this value will have some kind of chi-square distribution like this, and so if this value was shown, is found to be like this value, then we can compute whether this falls inside our rejection region or not. So in this case, this is our chi-square distribution, and then suppose alpha was 5%. In this case, let's so this is a two-sided test, right? We have to split them into half and then distribute it into either side. So this guy is a 2.5%, and then also this part will also have a 2.5% of the probability, right? Okay, and then if our statistic is falling into this rejection region, like this value or somewhere around this value, and then that's when we reject the null hypothesis. And then also the acceptance region will be like this statistic lying between these two values, right? And then that probability will be 95% in this case, right? And then what about this value? So in this value, this guy will correspond to this value, right? So this is a 2.5% of the probability, and then this threshold value is represented by this, right? But what about this value? What about this value? we have this probability as 97.5% of the probability, right? And thus it will be represented by 1 minus alpha over 2, right? So that is another threshold value, right? So that way we can determine our acceptance region. Then let's think about our p-value. Our p-value. So p-value has this kind of representation. So in the case of t statistic, suppose your value was found to be here, and in that case, in the case of two-sided test, we compute this probability, and also we consider the other side of the probabilities as well, and then we multiply 2 times this probability by 2, right? But in this case, the p-value in this case is represented by this. And then what does that mean in this case? What does that mean? So your statistic is called a C, right? So when computing the p-value, we do not consider alpha value in advance, so this alpha is not known. And then based on our statistic, we compute this threshold value, right? And then in the case of chi-square distribution, like this, suppose C was found here, okay? In this case, the probability will be something like this region, right? In this case, we can just multiply this guy by 2. So that will be our p-value. But what about your threshold value, or your test statistic was found around here? Was found around here. In this case, should you compute this part? Probably not, right? So in this case, you have to compute this probability and multiply it by 2, right? So in this case, it can be represented by, so this representation was shown to be, or found to be, more than 50%. So let's suppose this probability was found to be 75%. No, maybe 95%, for example. So in that case, this part will have a 5%, and thus the p-value will be 10%, right? And so in this case, we have to compute this value times 2, right? And so what we are doing here is we compute this probability like this, and also 1 minus this probability like this, right? So we are computing these two probabilities corresponding to the right side of the probability and the left side of the probability, respectively. And then we pick up, or we select the smaller one, okay? And then we use 2 times of this value as our p-value. Okay, so the time's up, so let's stop here and then continue this Thursday. Thank you.
과제에 대해 여기서요. 이게 지금 모수의 평균을 모수의 평균인데 이렇게 구하려고 인상 모니터 이렇게 구하잖아요. 근데 이게 지금 요세 가지씩 다 모수가 정규 분포를 이룰 때만 할 수 있는 건가요?
이게 이거 같은 경우인데 그게 맞는데 정확하게는 그게 맞는데요. 이 X 바 같은 경우는 이제 샘플 B잖아요. 샘플 B는 그러니까 근사적으로 이제 n이 크면 이게 노멀 디스트리뷰션이 따른다.
샘플 미니요.
그래서 이제 이거는 이제 샘플 민이 어떤 디스트리뷰션을 따르느냐를 가지고 이제 하는 거잖아요. 그 샘플 민이 이제 가우시안이니까 근사적으로 가우시안이니까 이게 이제 CLT 센트럴 리미트 티어럼에서 나왔던 거죠. 그래서 여기서는 그게 필요하지 않아요. 그러니까 이제 근사적이긴 하나 그 어떤 디스트리뷰션이든 이게 뭐 저기 바이노미얼이든 아니면 뭐 포화선 디스트리뷰션이든 아니면 뭐 그냥 뭐 이상한 디스트리뷰션이도 이거에 샘플 미는 기본적으로 가우시안을 따른다고 하니 그러면 이제 되는 거죠.
그러니까 그 모수가 정규 분포가 아니라도
아니어도
이렇게 할 수 있다.
샘플 미는 할 수 있어요.
근데 지금 여기서 구하는 이게 모수의
모수의 평균.
모수의 평균.
네, 모수의 평균. 네. 근데 다른 경우는 그게 꼭 가우시안이 필요한 경우들이 있어요. 그러니까 T 같은 경우는 가우시안이 필요하거든요. T로
모수가 가우시안.
네, 그러니까 우리가 이제 여기서 뒤쪽에 넘어가면 이게 T를 쓰잖아요.
예.
여기서는 가우시안이 필요해요. 가우시안. 그러니까 모수가 가우시안 디스트리뷰션이다라는 그 전제 조건이 그 가정에 필요해요.
이 경우에
두 번째. 네.
근데
그런 좀 서툴한 차이가 좀 있는데
문제를 풀 때 보니까 모수가 그 가우시안이라는 얘기가 없는데도 그냥 이렇게 이걸 여기 풀어야 된다는 뜻이 이렇게 써 있는 게 있는데 이걸 따져보지 않아요.
네네네. 근데 첫 번째는 일단 가우시안이 없어도 되고요. 두 번째는 가우시안이 좀 필요해요. 두 번째. 그리고 만약에 어떤 문제에서 이런 예제나 어떤 이런 문제, 뭔가 좀 수학적으로 뭐 증명을 하거나 이렇게 유도를 하거나 뭐 그런 거면 모르는데 그냥 그 예제 같은 경우는 그냥 대충 다 가우시안이라고 그냥 가정을 하고 그런 얘기가 없어도 그렇게 푸는 경우도 좀 있고요.
이게 T 디스트리뷰션 쓸 때 표 보고 하잖아요.
네.
근데 이게 30을 넘어가면은 30이랑 똑같다고 가정하고 해요.
그런 경우가 있었어요?
이 문제 3회짜리 그래가지고.
네.
그냥 근데 이게 제가 그 연장된 표를 인터넷 보니까 40 이렇게 들이 있는데 보니까 이거랑 똑같거나 뭐 100 정도 되면 0.00의 차이.
그러니까 일단은 이제 T 디스트리뷰션이 기본적으로는 T에서 그러니까 디그리 오브 프리덤이 이제 무한대로 가면 T 디스트리뷰션의 정의가 뭐냐면 스탠다드 노멀 디스트리뷰션 나누기 스탠다드 노멀 랜덤 베리어블 나누기 그 카이스퀘어의 이거잖아요. 근데 이제 n이 커지면 이 아까도 봤듯이 그 카이스퀘어 디스트리뷰션 디바이디드 바이 n이 기본적으로 그냥 1의 수렴을 하거든요. 그러니까 이거는 그냥 그러니까 좀 어느 정도 n이 커지면 t가 그냥 z랑 똑같아져요.
정규 분포.
네, 정규 분포가 똑같아지고 거의 아마 30일 때 혹은 30 이후부터는 나오는 값이 굉장히 미미하다라고 했잖아요, 차이가. 근데 그 값이
아마 그냥 Z 값이랑 똑같을 거예요.
아, 그 정규분포 이렇게 끝으로 가면 이렇게 되니까
네네.
그렇게 이해하는 거죠.
그다음에
여기서 세트 여기 S를 n-1로 하잖아요.
네.
근데 이게 n-1로 하면은 그 뭐지 디바이드 분산이
네.
이렇게 해서 나오는 것이잖아요.
n으로 나누는 거? 아, 네.
요렇게 못 쓰는 거죠. n-1이 있으면.
그죠. 이거는요.
네.
그러니까, 자, 이거는 지금 뮤를 알아야 되는 식이에요. 그러니까 이게 지금 뮤거든요.
예.
뮤 x가
예.
이게 true가 이제 기대값인데 true 기대값은 참인 기대값이잖아요.
예.
그러니까 그게 필요한 거죠 지금.
예.
그리고 그게 우리는 이 샘플 베리언스 여기식에서는 뮤를 이제 우리가 모르기 때문에
예.
뮤를 모르니까 뮤 대신에 x바인 부정확한 뮤 대신에 값을 쓴 거잖아요.
예.
근데 요식이랑 요식이랑은 이게 이제 뮤일 때는 경우가 있지만, 네.
그러니까 지금 여기서 이게
네.
그 표본이 평균이잖아요.
표본 평균.
이 표본 평균을 여기다 이거하고 가정하고 하면 필요가 없는 거죠. 이거 그
네.
문제가요.
네.
오차가
네.
정보잖아요.
네. 네.
이거를 실제 값 값이 오차가 이제 측정값이니까 이 식을 이용해서 이걸 구해야 돼요.
네. 그러니까 이게 이 값은 이제 오차가 평균 0이다라는 말은 이 값이 이제 실제 값과 빼졌을 때 실제 값과의 차이로 보면 평균이 0이다라는 뜻이에요.
예.
그러니까 그 말은 무슨 소리냐면 이게 그냥 그 평균은 진짜 값을 따르고 라는 말이 똑같거든요.
예. 그러네요. 예.
그러니까 뭐
예,
똑같은
알겠습니다.
거죠.
예. 예, 알겠습니다. 감사합니다.
네.